They say we learn best from our mistakes, so it's typical to start a fatigue presentation with one of the biggest lessons. And my favourite lesson is the story of the de Havilland Comet. The de Havilland Comet was the first commercial jet airliner. It first flew in 1949, and actually it was quite successful. Its last flight, commercial flight, was in 1997, and if you include its military derivative, the Nimrod, the last flight of that was in 2011, so a 60-year sort of lifespan. In terms of aircraft of its type, it was 10 years ahead of its competition. The Boeing 707 first flew in 1958. It flew twice as fast as any other commercial aircraft of its day. It flew at 500 miles an hour. And for comfort as well as economy, it actually flew much higher than any other aircraft, at 40,000 feet. Now, it was built for comfort. Sir Geoffrey de Havilland, the company owner, really was taking his lead from luxury travel of the trains at the time. So he built it with large square panoramic windows, just like you would have in a train. Because it flew so high, it was the first airliner to ever have a pressurized cabin. And it pioneered the use of stressed skin construction that used both rivets and adhesive, so a hybrid joint. It was the first commercial airliner to store fuel in the wing cavities. First commercial airliner ever to have power-assisted flight controls. Strangely enough, they were hydraulic controls. Because the hydraulic controls took away a lot of the feel from the pilot, then it pioneered the use of a simulated control feedback as well. Things that we see in every airliner today, really. That was called Q-feel. And everything about it really set the design for pretty much every airliner until we get the new generation of composite airliners today. Of course, when you're pioneering something that is so revolutionary new in so many areas, you're going to get design challenges. And the biggest challenge for the Comet was weight. Weight was an absolute premium. De Havilland wanted to use his own jet engines that he'd bought the company previously. They were the de Havilland Ghost, but they were very limited to just 5,000 pound-feet of thrust. In fact, they were so worried that the airliner wouldn't get off the ground that the original plan even had booster rockets. So I'm not quite sure what they would have done about the noise abatement in those days. Because weight was a premium as well, it used a really thin fuselage skin. It was 22 gauge, which for European people is 0.64 millimeters, so really thin for a stressed skin fuselage. And the reason it wasn't painted wasn't to make it look pretty, although it did look pretty. It was actually because the paint would have weighed too much, and therefore they couldn't have carried as many passengers. Later on, you see that the engines were changed, the Rolls-Royce Avon engine. But actually, they weren't in production until 1950, a full year after the Comet officially launched. Now, there are a few failures early on in the life with wing design and things like that. But the real ones, the ones that we're interested in, were fatigue failures. The first one happened on the 10th of January on a flight from Rome in 1954. The aircraft, yoke Peter, fell apart in the sky, and all 53 passengers lost their lives. The initial conclusion was it was down to fire, an explosion in the air. But less than 3 months later, on the 8th of April, another flight, again leaving from Rome, this time to Cairo, also exploded, and 21 people lost their lives. And after that, the aircraft was grounded for investigation. What followed was the largest crash investigation ever undertaken. A water torture test was built, and an aircraft was taken out of service. It had already seen 1,230 real flights, so they're the ground-to-air-to-ground cycles. And what they did in this tank was start to simulate those ground-air-ground pressure cycles in the cabin. After just 1,830 simulated flights, they found there was a catastrophic fuselage failure. So that failure occurred after just 3,057 ground-air-ground cycles. And the conclusion was that fatigue, having sort of a ratio of about 3 to 1, that fatigue life could be estimated somewhere between 1,000 and 9,000 cycles to failure. If we look back at the very first aircraft that crashed, it had done 1,290 flights, and the second aircraft had done just 900. So that bore out the results of the water torture test. When we look back at the history, then the biggest thing that people remember is square windows give stress concentration, so we don't use square windows in aeroplanes. But actually, de Havilland engineers did know that, and they designed their windows and all of the fastenings around them to cope with those stresses. Reality was that that wasn't really what drove fatigue here. What was the biggest culprit fatigue was the original design was a hybrid joint. It relied on redox bonding with drilled riveted construction. But the actual construction of the first comets was punch rivets with no bonding at all. So why does that make such a huge difference? So I'm going to plot an SN curve, and we're going to look at SN curves today when we test materials. So on the y-axis, we've got the stress. So this is the amplitude of stress from the ground to air ground cycle. And on the x-axis, we've got the log of the cycles to failure, the number of cycles. Now what we find is if we've got a bonded joint, it's pretty much a bit like a binary one. If you drop the stresses low, it almost never fails through fatigue at all. But once the stresses get above a critical amount, then it will fail almost instantly. So it's a very shallow SN curve, very long lives at lower stresses, but just raise the stress above that critical level and it failed catastrophically. Now, if you add to that a rivet joint as well, then what you end up with is a bit like the best of both worlds. So the drilled rivet joint can cope with those high loads. But as we reduce the load, we see that it will still fail. And that's because with the rivet joint, it's starting to initiate cracks. And those cracks grow until we get a failure. If we've got a bonded and riveted joints, we can take advantage of both. So normally, under normal flight, we're using the bonding, which has a very high life. But if we get bad landings and things like that, or overloads, the rivets can take those loads without it breaking the bonding. Now, if we were to change that, as we did in the Comet, for a punched rivet joint, a punched rivet joint isn't as good as a drilled rivet. You see, with a drilled rivet, it's got a nice smooth edge, but a punched rivet has a rough edge, and those fatigue cracks can start a lot better with rough edges. So we find out, actually, when we look at the real fatigue life on that log axis, that it's significantly less than what the original design intended it to be. And this really is what caused the failure of the Comet so prematurely and early. Now, it's not that the engineers didn't know about fatigue. The de Havilland engineers knew very well about fatigue. Fatigue testing started really in about the 1850s. August Wöhler was looking at the progressive failure of railway axles. He was a clever bloke, was Wöhler. Not only did he invent the first fatigue test, he went on to lead the German railway industry and was actually a very popular and accomplished politician as well in Germany. So he invented the first fatigue test, and you can see a little illustration of this from the patent just down below. So what he did was he put two axles, into bending. So we can see those on either side. The spring applies the bending load, and then pulley D was applied to a motor so he could rotate the shafts. As I say, he was a clever bloke, so not only did he invent the first rig, but he also invented the first data logger as well, because a fancy arrangement with string and pen meant he could actually count the number of cycles without actually having to sit there ticking them away on his watch. So what Wöhler was interested in was a concept called fatigue strength. What he did was he found out with his mild steel shafts that if he was to drop the load to a sufficient level, then they would appear to survive forever. Fatigue would never be a problem. And we call that the fatigue strength. Now, that was actually all Wöhler was interested in. He wanted his shafts to last forever. They were rotating many, many cycles, and that was good. And we still use that today for shafts which are rotating a lot in their life, like crankshafts and camshafts and things. Later on, Another fellow called Baskin found that when you're in the finite fatigue regime, if you were to plot the failure points on log axes, you could draw a pretty neat straight line through those. And we call that today the Wöhler curve, or the SN curve, after Wöhler, who created the very first test machine. Now, Wöhler was testing mild steel under constant amplitude sinusoidal load, and it is true that you find that there is a fatigue strength threshold for mild steel under constant amplitude loading. But more generally, for most materials, we find that's not true. So if we looked at an aluminium alloy, for instance, we see a very definite change at that transition, but it's certainly not an infinite life that we see there. And even steel, under variable amplitude loading, we see that it has a gradient to that line. It's not infinite life, but we'll come to that later. As well as the Wöhler machine, we see these axial machines. So the photograph on the left there is showing a typical strain-controlled test on bar stock. So this is an hourglass specimen with a clip gauge attached to it, and you'll see lots of those in our lab if you were downstairs at the moment. Next to it, you see a slightly strange arrangement. We're not testing that great big fixture. This big thing around here is actually what we call an anti-buckling guide. So this is a strain-controlled test. The clip gauge is actually round the back, and this is of a thin sheet of material which we're going to go fully compressive and tensile with. So we need to resist that buckling. And again, if you went down to our lab today, you'll see different types of design for anti-buckling. This one's actually carrying quite high loads, so you'll see that it's actually got PTFE guides around it to provide a frictionless surface. Some of the others, which have lower loads, actually use an air gap as a lubricant around there. About 0.1 millimeters it tends to be. But you'll see those sorts of things. Again, if you were to look at a typical rig, it looks something like this. The thing that dominates the rig that you notice first of all is the test frame around it. You'll also notice that we have a hydraulic actuator that applies the load. On this one, the hydraulic actuator is at the bottom, but it could quite as easily be a top loaded rig as well. The specimen goes in the middle, and at the end we have a reaction. So what we do here, if we look at the sensors, then on the typical test rig, there is first of all a load cell. This is measuring the load that goes through the specimen. We have an LVDT, so this is a linear variable displacement transducer. It's measuring the displacement that's applied to the specimen. And in this case, we also have a clip gauge, an extensometer or strain gauge, if you like, that's measuring the strain that's going into the specimen at the critical section. Now, one of the main things with a test rig is to keep your component actually aligned. You want perfect alignment. And in this example, you can actually see a Woods metal pot being used. So Woods metal is a bit like solder. It's a low melting point metal. We heat it up, in this case, under boiling water, and then we can lower the specimen and the end grips into that. Then we can cool it off, and it sets to form a hard metal, but we get perfect alignment. It takes a little bit longer with Woods metal to set up each test, but the benefit is the alignment is better. So we tend to use those wherever we can. Now there are three, as I say, sensors. There's the load cell, the clip gauge, and the LVDT. And through our control system, we can control it through any one of those three. And today what we'll be looking at is load control testing. So this is effectively sending a command signal, like the triangular signal that you see in this controller, and we want the load to actually follow that command signal. The other thing we could do is to look at strain as well. So we could use a clip gauge and do a strain controlled one. Or we could do a displacement control as well. I won't talk about those today. Load control or stress and strain are by far the most popular. A few other things that you'll see as well. If you go down in our lab at the moment, it always ends up that in the height of summer is when we do the hot testing, because that's when it comes in. So we can have furnaces. On the left, you can see an induction furnace. These are used for heating components very, very quickly for things like thermomechanical type loading. On the right, you can see a more conventional furnace. These go up to 1,000 or 1,400 degrees, and they're heated in 3 different zones, and they're controlled to get exactly the right temperature. As well as going hot, then we can go cold and humid too. So this is a picture again of an environmental chamber. So this we can control the temperatures between -50 and +150, and it's also got full humidity control. And if you were to open the door to this today, you'll see that there are engineering polymers and things like that that we can test in that, which are particularly sensitive to humidity. Okay, so we've had a little virtual tour of the lab. We've seen what a rig looks like. Let's have a look at the analysis then that we need to do. And we're going to start off by looking at load control. So this is stress control, if you like, load control. It's where we're deriving an SN curve. So in this case, if we were to look for a typical rig set up for load control, we actually see that it's a specimen like this hourglass specimen. We give it a command waveform. We can see here that we've got a sinusoidal stress profile. And what we try and do is we try and plot the number of cycles to failure on log axes. And we see here, if we start to look at that, we can start to see this straight line forming through there. And we can represent that using a simple equation. This is the Baskin equation. It's the equation of a straight line in log space. Now, when we try and fit a curve, just two things to remember. First of all, an SN curve is not a single straight line. Typically, as we'll see in a minute, the SN data has three distinct regions. So make sure when you're fitting a straight line, you're fitting it through the correct region, otherwise you're going to get the wrong results. And the other thing is, if you come from a reliability background, a fatigue test, an SN test, is not the same as a reliability test. You can't use MLE and use the suspended tests for that. So what that means is normally in a reliability test, if the test is suspended because you've hit the run-out limit, then you can still do some nice statistical trickery using probability to include those results in your analysis. But with SN, you can't do that. And that's simply because it's a different failure mode when you get into those post-endurance. So you can't imply that the same statistical distribution was present from the other tests. So that's just a little word of caution for you there. Don't treat these as suspended tests in fatigue, because very often run-out are a different physical failure mechanism. So when we look at these typical data then, we find that they fall into these three distinct regions. At the top, there's the plastic region, there's the elastic region in the middle, and then there's the post-endurance region after that. And they're characterized by sort of two transition points. The transition life is the one that differentiates between plastic and elastic. And typically this lies somewhere between about 1,000 and 10,000 cycles to failure for most metallic materials. Further along than that is the endurance limit. So this is either the endurance, the infinite life one, if you've got mild steel under constant amplitude loading, or in aluminiums we call it the endurance limit simply because there is a change of gradient. And they're typically lying between about 10 to the 5 and 10 to the 7 cycles. Beyond the post-endurance is a different slope, and we can test that using high cycle or vibroacoustic testing. But in general, a lot of people aren't particularly worried about that life and characterizing it, so there are also correction factors we can apply too. So either it can be infinite life, it can carry on the same gradient, which is conservative, or after high back, for instance, there is a correction factor where you can estimate that if you've not gone to the expense of measuring it. So when you're fitting your straight line in whatever software product you want to use, then make sure that you're only fitting the bit that's in the middle, the elastic region. If you want to characterize the post-endurance region at the very high cycle, there's another technique we can do. It's called staircase testing. So this is where we're trying to find a fatigue strength. So the first thing we do is we establish an endurance limit in our design. So it's very often something like 1e to the 6 or 1e to the 7 cycles. That's where we define, if you like, what our infinite life is going to be. Then, based on our SN analysis, we can estimate what we think that fatigue strength is going to be. So in this case, I'm going to use, say, 100 megapascals, as it's a nice round number, just as an example. We also need to set our precision interval as well, delta S. So in this case, I'm going to be, say, a resolution of 5 megapascals is probably fine. And the way that we proceed is this. We do lots of tests, almost to destruction. So let's set our first specimen in the rig, and we're going to target it for 1e to the 7 cycles. Now, our first one here actually failed before that target. So what we do now is we reduce it for the next test to just 95 megapascals. So you see that in that diagram on the right. And we test it again. And in this case, we see that that new specimen also failed before it hit the 1e to the 7 target. So now we repeat the test with another new specimen set to 90 megapascals. This little red square indicates that this survived. So it survived the 1e to the 7. So we take that out, we put another new specimen in, and we test it now at 95. And by doing this staircase analysis, you can see that you can start to establish where the fatigue strength is with a given reliability and confidence interval. And the approach that we would take in that is something like a Dixon-Mood or Stenson-Lauren type statistical analysis in order to establish what that fatigue strength is. Now, SN analysis works really well in the elastic range, but it doesn't work very well for plastic loads. We call those low cycle fatigue, where we've got plasticity introduced. And the reason for that is because we're measuring the elastic stress, when actually the thing that's driving fatigue is the shear strain energy. So strain energy is actually the area under the cyclic stress strain plot, the one that you see in this loop here. Now, you'll start to see as the stress increases and we go plastic, a tiny change in stress makes a huge change in strain energy. So what we find is that that zone, when we're in the SN curve, is very shallow because we lose resolution. Tiny change in stress has a massive difference in fatigue life. So if you're really interested in that, rather than using stress, it makes sense to use strain instead. Because if you think about it, a small change in strain will create a smaller change in life. And you need to create a big change in strain to get the big changes. So typically we only use SN up to the elastic limit, and beyond that we need to use strain, because strain is much better related to the component that's really doing the damage, which is strain energy. And that really is where EN, or strain controlled testing, came in. It allows us to consider those low cycle fatigue, those high amplitude cycles, which may only occur once every blue moon, but they do create exponentially more damage. So how do we test those? So here you can see what happens. Our elastic line is that Baskin equation. So now on the y-axis it's strain rather than stress. And if we look at that Baskin equation, all we've done is taken the SN curve and divide it by E, Young's modulus, to turn it into an elastic strain. What we've then done, though, is we've added this other part to it, this Coffin-Manson part, epsilon f prime times 2nf to the power c. That's what we call the plastic line. And now what we see is we're now measuring strain amplitude. So it'll take, to get a change in fatigue, takes a much bigger change in strain. And that means that we can start to plot with far more precision what's happening in that low cycle, but high amplitude fatigue range. So in strain life, we actually need not just a curve, a fatigue curve, but we also need that relationship between stress and strain. And the reason we need that is twofold. Firstly, when we consider things like mean stress correction, if all we're doing is measuring strain, we need some way of finding the stress in order to do the mean stress correction. But the other thing is, most FE users will do a linear analysis in FE even though there may be some local constrained plasticity. So we'll probably want to use something like Neuber's rule to turn that linear measurement from Fe into an elastic plastic measurement for this. And again, that cyclic stress strain curve allows us to do it. So how do we fit the cyclic stress strain curve? Well, we use a simple approach. It's an equation, a model called the Ramberg-Osgood-Neuber flow rule. So if we were to plot the stress strain through the linear and the nonlinear range, we can start to see it follows either that red or that green line. And what the Ramberg-Osgood model does is try to fit a simple equation through that. And the equation is simply, we know in the elastic regime that the elastic strain is simply the stress over the modulus of elasticity. So what we do is we add a plastic component to that as well. That one we model as stress divided by K prime raised to the power of 1 over M prime. So you can see what we've done. We've fit a straight line in log space through that. And we see that in that right-hand plot. So the way that we find this, the parameters for this Ramberg-Osgood is simple. The first thing we do is we look at the low stresses and we fit the elastic line through that. We find the modulus of elasticity E. Then when we get to those higher stresses where there's plasticity involved, we subtract the elastic part and we plot on log paper the remaining parts. And if we fit a straight line through those, we can then find out the K prime and N prime. So all we're doing again is fitting a straight line in log space. So how do we do the fatigue part? So for every test that we do, we capture the stress and strain information. So we can see here a typical sort of plot. I'll try and get a laser pointer up. There we go. Laser pointer. So on our top plot here, we can see the strain, how it evolves with time. Now these are strain control tests. So at the beginning here, we can see that we've got a very quick soft start effectively, so that control system keeps up with what we want. And then it keeps perfectly straight as we have, because we're in strain control. The controller is controlling the strain. Over here though, we can see the result from the load cell. So first of all, it stabilizes. Sometimes we see some plastic hardening or softening occurring here in some plots and some materials. We then stabilize, and then what we see here is a load drop. The load drop's occurring because a crack's starting to grow, and so it requires less load to achieve the same strain. And if we plotted the stress-strain hysteresis loops, we can see that in the green one here, look. So the strain amplitude, the difference from left to right, is always kept constant. But the load it can carry is reduced simply because the crack's forming. And we see there's a different shape to that in the compressive region here, where the crack closes and comes together, from when the opening one, where we're opening up that crack. So typically, what we do is we look for a particular load drop. Different people have different ones, either 10% load drop or 20% load drop, and that's when we define that the crack's sufficiently long that we've reached the end of the initiation life. The other thing that we take away from these tests is usually about the stable point in the middle of the test, we capture the loops. So in this case, it's probably going to be about the blue loop. These are the stabilized loops. And what we're interested in here is what was the elastic strain and what was the plastic strain. So the total strain is the distance from left to right here. From this loop, we can see where it crosses the zero stress line, then that becomes the plastic strain. And if we take one from the other, that gives us the elastic strain. And we use those two values, elastic strain and plastic strain, when we fit the Coffin-Manson equation down here. So when we characterize it, this is what we do. We start off first of all by characterizing the Ramberg-Osgood, the cyclic stress strain plot that you can see here. What we then do is we find the life based on the load drop, and then we start fitting the elastic line. So we take the elastic strains and we now fit the Baskin equation, the sigma f prime and the b for those elastic. We then take the plastic strains that have separated from that analysis we did before, and this allows to fit epsilon f prime and c. Now, typically, what we need to then do is add them together, and they usually add together quite nicely to fit the entire curve, but we usually do a little bit of re-optimization on these parameters, just so it fits, especially better in the middle where the two are added together. Once we've got a good fit, we then start to do an outlier analysis. In an outlier analysis, we're looking for points which don't lie on that curve. Now, some that's going to be just statistical scatter, and we're going to use those in our design curve, so we're not worried about those. But some of them are clearly indicating that they don't lie on that regression line. And that's very interesting. We need to know, why is that? Can we exclude them? Have they failed in the grips or something like that, which makes it an invalid test? Or is it really a valid test? And what we're looking now at is characteristics of the material as well. And these characteristics could be fed into your components. So we need to characterize that spread if that's the case. We also have the option in some cases where if we can't exclude the test because we can't see a reason for it being invalid, but clearly it's biasing the curve, we may take it out of the regression test, but we'll include it still in the scatter that we use to derive those design curves. So there are three options with outlier analysis. We can exclude the point, we can include it fully, or we can exclude it from the curve fit, but include it in the scatter that goes into the design curve. Okay, so what is the design curve? Well, that regression curve is the best fit curve through the data. We call that the 50-50 or the B50 curve. And what that's telling us is that half of your samples have failed at that point. So we don't necessarily want to use that for designing things. So instead, we create a design curve instead. So this is using so many standard deviations from that regression curve in order to look at it. So if we went for, say, a 95% reliability curve, that means we're getting the 5 failures in 100. If we went for something like a 99.9997, then that's about 4.5 sigma, that's 3.4 failures in 1,000,000, and so on. So, and 6 sigma would manifest itself into about 1 failure in 1 billion. Now, it's worth pointing out at this that most people, when they're looking at a design curve, typically look at something like a 97.5% design curve, or 95% actually as well. Now that sounds like that's a lot of failures. If you're going to be producing 250,000 cars and you're expecting 2.5 failures in every 100, then that's an awful lot of warranty claims, for example. And we dread to think about what would happen in aircraft. The reality is, though, that this is just one statistic in many. So we're applying this statistic to the materials. We've also applied statistical safety factors to our stress analysis, safety factors to our load calculation, and everything else downstream as well. The important thing is to make sure that when all of your statistical reliabilities are combined together, that you're achieving that failure rate that you want, maybe a 6 sigma failure rate, 4.5 sigma, for instance. It doesn't mean that every single statistic down that stream has to have that same level. So typically people ask for 97.5 or 95% reliability curves. Now, as well as the reliability, there's also a confidence band. And the confidence band is set by how many tests you actually did. So what we're looking at, if you imagine, we're looking at the deviation from the mean, the regression curve. Now, if we need that standard deviation, the more points we have, the more confident we can be in the number. If all we've got is 6 points, then the standard deviation that we estimate could be wildly inaccurate. The more points we have, then the more sure we have of it. So we have two options here. One, if you want to get more accuracy, then put more points in and do more tests. If you want to demand more confidence but not change the number of points, you have to add a safety margin instead. So it becomes a challenge as knowing how many points are the optimum. Adding extra points in doesn't improve your safety margin, but if you have too few points, then you need a big safety margin. So again, there's a study, and I'll talk about this later and introduce you to it, where we look at that analysis of how many is the optimum number of points in an EN curve. There's another question I just want to hit at before we get to those case studies. And this is, do you move the curve left to right along the cycles to failure axis, or do you move it up and down along the stress or the strain axis? And we have this, the reason I've got this as a slide is because this is a question that we get on an almost monthly basis. The reason that this is complicated is that the statistician will answer one way, but it really depends on how the equation's written. So the statistician's answer, and them being quite right, is true, that the strain amplitude in this case is the independent variable. In other words, that's the one we know is true. We set our rig up with the strain amplitude fixed. It's constant. That cannot vary statistically. So in theory, there's no way the curve should move up and down. The variable, the dependent variable, is life. That's the thing that changes statistically. So the curve, in theory, should move left to right, dependent on the reliability that we're after. In fact, when you do an SN analysis, that's exactly what we do. We move the curve left to right in terms of its reliability statistic. However, in strain life, we move it up and down. And the reason we do that is because the strain life equation, the Coffin-Manson-Baskin equation, is a transcendental equation. We can't rearrange it in terms of NF as a simple function of strain. So in this case, we apply a separate scatter factor effectively on the plastic and the elastic sides, and that effectively moves it up and down. But whether you're moving it up and down or left and right really doesn't matter, providing you're consistent in the way you're measuring your statistics. So if you're using your own software to do this, make sure that if you're putting it into our software, that stress life SN, the curve moves horizontally, so your standard error value will come from your cycles to failure. But in EN, then your standard error value comes from the strain, the elastic strain or the plastic strain that we're using. If you've still got more questions on that, then we can talk about those when we're finished. So I just want to finish now with a couple of case studies just to show you some of the work that we do on a regular basis. So my first one is the experiment that I talked about earlier on sample size. How many material samples do I need to get a good design curve? This happens all the time. Whenever a new customer who's new to fatigue or new to testing comes along, they say, how many samples do I need? And very often they turn to things like ISO standard or the ASTM standard, and they come up with a number of about 15. However, is 15 the optimum for a design curve? So in this experiment, what we do is we've obtained a candidate material, a very common mild steel in this case. We've tested a very large number of samples, in this case 44 samples. And we've derived a design curve for that full population. We've then taken several random selections from that full population and compared it with the design curve. And what we're trying to do is to find a point when the design curve becomes economically optimum, i.e. adding more points doesn't improve it any, but if we drop points, then the safety factor becomes large. So here we can see the full family of 44 data points. You can see the nice fit there. You can see the red line here is that 97.5, 95 design curve. And here you can see the fit through the elastic and the plastic points. Now here you can see what happens when we reduce the number of points. So if we have 6 points, then clearly that is the minimum that we can use to fit 2 straight lines through it. So the design curve here is very low compared to the other one. If you look at it, it's moved quite a lot over because of that. Actually, the bigger problem with 6 data points is it's almost impossible to get 6 data points aligned evenly along the curve. They tend to come in clumps. So what you find is that certain part you'll get lots of points together, but then you end up with big gaps with nothing at all. So you've got no confidence in those. 8 points is pretty much the same story, and so's 10 points. It isn't until we start to get to 15 points, which is typical ASTM ISO territory, that we've got a good chance that we get a fairly even distribution that we're looking for. But at 15 data points, then unless it's perfect, our design curve is still quite a high safety margin off it. In fact, what we find is typically we need 20 to 30 points before we end up with this economic optimum. So at 15 points, we could get there, providing it's evenly distributed, but usually it's not even. By the time we get up to typically about 25 points, that's really where we get the optimum design curve for about 97.5, 95 curve in that. Adding more than that isn't necessarily going to help us. If we take less than that, then what we find is that we start to either get bias in the data, or we start to get a significant safety margin because of the design requirements that we're looking for. Here's another case study. This one came about quite a lot over the past few years. An old material no longer meets environmental standards. The one I'm thinking here is hexavalent chromium, where we've reduced the chromium content significantly in stainless steels, and we're now looking for replacement steels, which probably aren't as good. We need to find out whether they're suitable for fatigue, though. So our approach here is we do an EN test of the old material. We know this didn't suffer at all from fatigue. We'll do a test of the new material. And if that new material is better than the old one, everybody's happy. The problem is, very often, it's not quite as clear cut from that. So in this particular problem, our customer here didn't know the service loads of every component that they'd manufactured. It wasn't possible to measure it. So again, we had to use statistics. So this is an ideal situation. The old material is shown in blue, and the new material is shown in red. So the red circles are the new material, and clearly they're showing much better life than the old ones. So in this case, there's no problems. As an engineer, we can sleep well at night, knowing that the new material has less scatter, and it's got a better fatigue life than the one it's replacing. So therefore, there's little to worry about, hopefully. However, this is typically what we find. So again, the blue squares are the old material, and this appears to have a better fatigue curve, a better regression line than the new material it's replacing it with. So straight away, we can't really, with any confidence, say that the new material is a suitable replacement. We need to do more fatigue analysis, more statistical analysis. Now with this material, which was based on a real example, the customer didn't know all of the loads. However, they did know that in the past 15 years, no components had failed. So we can start to work out statistically based on this data, if no components have ever failed, then we're pretty sure that our working loads must be below this area, because statistically, with a good confidence, we should have seen some failures if they were higher than that. So effectively, we're using statistics just to try and work out where the working load range is. It's somewhere down here. Now, if we start to look at that, so that's got a lot of scatter. We notice that old material, a statistical scatter is high. If we look at the new material, even though the regression line is poorer, in terms of its constituency, how well it constitutes the curve and how the scatter, we find that its scatter is a lot less. And we find this a lot with new material. As quality processes in the manufacture of materials is improving all the time, what we find is that the scatter is diminishing. And this is what we're seeing in this replacement material. So now, with the same sort of confidence, we can see that even though the regression curve was below, in terms of its design curve, it's above. And that's because it's a more consistent quality of material than the old one. So in this case, with a 98% confidence interval, we can actually say that the new material is at least as good as the old one, even though the regression curves don't match. And finally, the last case study I want to consider, this again is a common problem. This was from one customer. He said he used more than 20 different materials in all their components. He said no materials have ever been tested in living memory within the organization, and he was also certain that some were Googled, using his words. He's changed suppliers several times, and his question to us, I'm worried, but what should I worry about first? So the first thing we did was to say, okay, we can't go and test all more than 20 materials in full for you. That's a very expensive test, so let's shortlist them. So first of all, let's consider, is the design curve that you're using so far, is it still safe to use? Because if it is safe, you might not want to prioritize those. Then we'll start to look at, does that current design curve really represent the material you've got? If it's very conservative, then you might want to retest it anyway because you're over-designing components. And as I say, materials are improving in their quality, so the design curves are going up all the time. And the idea is to create a prioritized list for testing. So the way we did this was to use small samples of tests. Now, if we were trying to characterize a material from the ground up, as we saw earlier, you need at least 15 to get the regression curve, typically 25 if you want to get a design curve from that. But here we're using small numbers of tests just to start to see how far out are we with the data that they're using. So here we've got a comparison of new material B with the original design curve. So if we've got the design curve, we can start to see that. And here we've done a 10% significance on these bands, and we can see that material B, first of all, it's not the same as material A. So when we do this, we do it in two parts. The first thing we start to do a test to see, statistically, is this the material from this population? So is material A and B, are they the same? If they are the same, that's fine. If statistically they're not the same, we can go on and say, can I, with any confidence, infer that the new material is better than the old material? So in this case, we do accept that they're different, but we can do an analysis, and this analysis actually shows that we have a 98% confidence that the new material is better than the original material, even though we've used just a limited number of samples for that. So using this sort of approach enables us to go and explore lots of materials and prioritize those. Other areas where we do a lot of this is where we're looking, particularly in things like motorsport, where they're looking for new materials to replace old ones to get ahead of their competitors. And so what we're looking at is comparing different recipes of materials to see how the fatigues are, so that we can shortlist materials which can be used for later production and research. So in conclusion then, I hope you've enjoyed this webinar today. We've had a look at an introduction to metal fatigue, and we've looked at a horror story, my favorite one, the de Havilland Comet. We've also looked at how we can characterize materials for their statistical reliability and confidence. And we've considered the SN approach and the EN, the stress life or Wöhler approach and the strain life models. And we've looked at 3 case studies. We've looked at how many specimens to test. And basically we've said if all we want is a regression line, 15 specimens is probably your minimum. But if you want a design curve, then you should be looking about 25 specimens at least. Otherwise, you'll end up with big safety margins coming in or problems with biasness in how that curve's distributed. We've also looked at an example where we've validated replacement materials or plug-in replacements for different materials from different suppliers, even if they don't necessarily know what the original loading was. Now we've looked at examples of how we can use simple statistics to help us prioritize testing.